In this lecture, we will discuss surjective, injective, and bijective maps. First, we will review some concepts involving functions. Let's define the following. Let capital X and capital Y be sets. We use the notation f from x to y to denote a function, where f maps little x to little y means that f of x is equal to y for each element little x in capital X. The set capital X is called the domain of f, whereas the set capital Y is called the codomain of f. Again, let f be a function from capital X to capital Y. We'll define the set f of capital X to be the set of little y in capital Y, such that little y is equal to f of x for some little x in capital X. This is a subset of the codomain Y. It is called the range of f or the image of f. Again, take f from capital X to capital Y, a function. For any subset u in Y, the set f inverse of u is defined to be the set of little x in capital X, such that f of little x lands in u. This is a subset of the domain capital X. It is called the preimage of f or the inverse image of f. Note that f inverse is not itself a function. Here is a diagram illustrating the definition so far. So notice on the left-hand side, there is a red oval marked capital X. This is the domain of the function f. On the right-hand side of the diagram, there is a blue oval marked by capital Y. This is the codomain of the function f. Also on the right-hand side, there is a yellow oval. This is the range or image of the function f. And the arrows going from left to right represent the function taking little elements x in capital X to their image f of little x in the range of the function. We will say that f is well defined if f of x1 equals f of x2 whenever x1 is equal to x2. Sometimes we call this a morphism. For example, consider the function f from q, the rational numbers, to z, the integers, defined by a rational number written in the form p over q, where p is the numerator of the rational number and q is the denominator of the rational number, maps to just the numerator p. This map is not well defined because, for instance, if we take x1 is the rational number written 1 over 1, and x sub 2 is the rational number 2 over 2. Of course, these are the same rational number, yet according to our definition of f of x sub 1 is the numerator of x sub 1, which is 1, and f of x sub 2 is the numerator of x sub 2, which is 2. So for the same input, we get two different outputs. Now you might ask, well, perhaps we should not have started with inputs that had a common factor in the numerator and the denominator. And this is exactly the point of having this notion of a well-defined function so that we get an unambiguous answer. We say that f is an injection if f of x1 is not equal to f of x2 whenever x1 is not equal to x2. Sometimes we will call this a monomorphism. For example, consider the function f from the real numbers to the real numbers, defined by little x maps to little x squared. This map is not injective because x sub 1 equals minus 1 and x sub 2 equals 1 are different inputs. Yet, if we apply the function f to x1 and to x2, for both the squares are equal to 1. So the outputs are the same. We say that f is a surjection if for each little y in capital Y, there exists little x in capital X, such that f of little x equals little y. Sometimes we will call this an epimorphism. For example, consider the function f from the real numbers to the real numbers, defined by, again, little x goes to little x squared. This map is not surjective because there is no little x in R, such that, for example, f of little x is equal to negative 1. We say that f is a bijection if it is both an injection and a surjection. Sometimes we will call this a bimorphism. One remark is that we will reserve the words homomorphism and isomorphism for later when we introduce maps which preserve a given binary operation. Okay, let's consider some examples illustrated as follows. So in this first example, the domain of the function x has the numbers 1, 2, and 3, mapping to this codomain, capital Y, with the letters A, B, C, and D. So in this diagram, we see that the function depicted is not surjective because, for example, the letter capital C in the codomain of the function, there is no element of the domain that maps to capital C. So since it's not surjective, it's also not bijective. Okay, here's another example, this time going from the numbers 1, 2, 3, 4 in capital X to the letters B, C, and D in capital Y. This time, the function is not injective. So for example, we see that 3 and 4 are two different inputs, yet both of these elements of the domain map to the same element, capital C, in the codomain, capital Y. So this function is not injective and therefore also not bijective. In this last diagram, we have the numbers 1, 2, 3, 4 mapping to the letters A, B, C, D. In this diagram, in this function, we see that the map is both injective and surjective. So injective, if the inputs are different, then the outputs are different. Surjective, each element in capital Y, for each such element in the capital Y, there exists an element, little x in capital X, that maps under the function to that letter. So it's both injective and surjective, and therefore bijective. Let's consider the following proposition. Let f from x to y be a well-defined map. Then the following are equivalent. First, the map f, we say, is a monomorphism. This is the same thing as saying that the map f is injective. Third, the definition is that if x1 is different from x2, then f of x1 is different from f of x2. This happens if and only if the map F has a left inverse. This means that there exists a function g from capital Y to capital X such that g composed with f from x to itself is the identity map. Next, we'll consider a similar proposition for surjective functions. So let f from x to y be a well-defined map. Then the following statements are equivalent. The map F is called an epimorphism. This is the same as saying that the map F is surjective. The definition of this is that for each little y in capital Y, there exists little x in capital X, such that f of little x equals little y. This happens if and only if the map F has a right inverse. And the definition of this is that there is a function h from y to x, such that f composed with h from y to y is the identity map. So note that the composition in this proposition is different in a different order than in the first proposition. Next, we'll explain the relationship of the concepts that we've seen already to concepts from linear algebra for those who are familiar with linear algebra. Suppose we have a linear transformation T from f to the n to f to the m, where f is either the real numbers or the complex numbers. So T sends a vector x written as x1, x2, up to xn. It maps it to this vector y in f to the m, written as y1, y2, up to yn. So we know that this linear transformation is the same as multiplying a matrix A by our vector x. So the matrix A is an m by n matrix with coefficients in F. Proposition. By the rank nullity theorem, we have the following statements are equivalent. This linear transformation T from Fn to Fm is injective, i.e. a monomorphism. It is equivalent to saying that the kernel of T is the trivial subspace. So the kernel of the linear transformation T is defined to be the vectors little x in f to the n, such that T of little x is equal to the 0 vector. So we're saying that this subspace is the trivial subspace. The next equivalent statement says that the rank of the m by n matrix A is n. Next, we have equivalently that there exists a linear transformation S from Fm to Fn, sending y to b times x, such that S times T is the identity transformation. And finally, there exists an n by m matrix B such that B times A is I sub n, the n by n identity matrix. Okay, let's repeat this for a similar proposition using the rank nullity theorem for a surjective linear transformation. So we get the following statements are equivalent. T from Fn to Fm is surjective, i.e. an epimorphism, is equivalent to saying that the image of T is a non-proper subspace. So the image of the linear transformation T is defined to be the set of vectors y in f to the m, such that y is equal to T of x for some vector x in f to the n. And we're saying that the image is non-proper, so it's all of f to the m. An equivalent statement is to say that the rank of the m by n matrix A is m. Also equivalent, we will say that there exists a linear transformation F from Fm to Fn, sending y to b times x, such that T times S is the identity transformation. And the last equivalent statement is that there exists an n by m matrix B such that A times B is I sub m, the m by m identity matrix. Okay, Now, using these ideas of functions, we will talk about a certain kind of function called permutation. So let's assume that we have F a well-defined map. Then the following statements are equivalent. The map F is a bimorphism, or we say that the map F is bijective. This is equivalent to saying that the map F has a two-sided inverse. So this means that there is a function g from y to x such that both g composed f from x to x and f composed g from y to y are the identity maps. We call g the inverse of f and denote it by f to the negative 1, or f inverse. A permutation of a set X is a bimorphism or bijection sigma from X to itself. Next, we have the following proposition. Given a set X, let's let S sub X denote the collection of permutations sigma from X to X. Then the identity map 1 from X to X, which sends each element little x to itself, is a permutation. If sigma and tau from X to X are two permutations, then their composition sigma composed tau is also a permutation. Moreover, we have the following formula for the inverse of the composition. So if we take sigma composed tau and take the inverse of this composition, that's equal to tau inverse composed with sigma inverse. With composition from a pair of permutations to a permutation, this pair of S sub X with composition forms a group. Thanks for watching.